Hi everyone, and welcome to this first video on a series I'm making about number theory. In this, properly zeroed video, I hope to give some motivation and a glimpse of what we'd like to study in number theory. At its heart, number theory is the study of the integer ring Z, and there's various methods we can use to approach this: analytic, algebraic, the deep confluence between the two. To refine what we mean by the study of the integers, we notice the fundamental theorem of arithmetic, a fact we know and love. This affords unique factorization at the level of elements, so into primes, up to a unit. Give me any integer, I can express it uniquely up to plus minus 1 as a product of prime numbers. So naturally we'll focus on the study of primes, and that's really what number theory is about. At a ring theory level, for p prime we consider the ideal it generates, all multiples of p. This is maximal, expressing that the integers have kernel dimension 1, every prime ideal is maximal. When we mod out by these prime ideals, we get finite fields, f sub p, of order and characteristic prime. We look at the fraction field of the integers, which is the rationals, and the rationals alongside this collection of finite fields constitute the prime fields, which are foundational because either the rationals or finite fields embed into some general field k, depending on the characteristic. In the former case, it's if and only if k has characteristic 0, in the latter if it's a positive characteristic or prime characteristic p. So this is at a basic level. When we're studying the primes, we can also look at their distribution and density, as well as their growth. So this is accomplished in part by studying the Riemann zeta function, which is a function of a complex variable s initially defined real part of s greater than 1 to avoid convergence issues. We'll look at how this extends from a function initially defined on a half plane to the entire complex plane, and the beautiful symmetries and information that emerges from completing the function over the entire complex plane. It's defined as the sum over 1 over n to the s, n greater than 0. And Euler found this wonderful formula where the zeta function is actually equal to the product over primes of 1 over 1 minus p to the negative s. Already this affords us a new proof that there are infinitely many primes. Why is this? Well, if we take s equals 1, then we notice this left-hand side diverges because that's the usual harmonic series. But if there were a finite set of primes, and those were all of them, this right-hand side would form a finite product and it would converge. But we can't have something divergent on the left-hand side and something converge on the right, which means there would have to be infinitely many primes for this to still be true. Okay, so this is the zeta function, which I'll come back to in a moment. We can also look at, for a more general theory that affords a very robust selection of so-called number fields to study from, finite extensions of Q. An example of this is Q adjoin the imaginary unit, which we get by taking the polynomials over Q and modding out by something like x squared plus 1. This is a maximal ideal, and of course when we mod out a ring by a maximal ideal, we get a field. That's this Q adjoin I. We look to study the arithmetic and properties of these number fields, as well as their analogs of integers. So how do the integers generalize in these extensions of Q? And number fields they're one of two types of what are called global fields. This will be an important subject, looking at what is a global field, what characterizes them, what sorts of properties they have. But naively, we can just say that global fields consist of finite extensions of the rationals and function fields, which are finite extensions of rational functions over a finite field fq. Why is this a reasonable thing to do? To put number fields and function fields on a similar footing, so to speak? Well, we can trace this back in part to the arithmetic similarities between the integers and the polynomial ring over a finite field. First, let's notice they're both principal ideal domains of dimension 1. So this means that every ideal is generated by one element in each of these two rings, and every prime ideal is maximal. Furthermore, they have finite groups of units, where the units in the integers are just plus minus 1, and in polynomials over a finite field, it's just the elements in the finite field themselves. So they're Q such in this case, and in both they're finite. There's 2 here, and there's Q on the right-hand side. When we look at quotients modulo prime ideals, we get finite fields. So for Z, we looked at these f sub p, p prime, and for this ring, we get finite fields of the form f sub q to the d of order that is some power of f sub q. And in both rings, there are infinitely many primes. For here, they're afforded by the prime numbers, and the natural generalization or analog of prime numbers in these polynomial rings are just the irreducible polynomials. So there are infinitely many such in both rings. And these four facts, taken all together, shed some light as to why we can pass to the analogy between their fraction fields. In the first case, it's going to be the rationals. In the latter case, it's the rational functions. So we will study the very deep and profound analogy between these two kinds of fields and point out their differences when necessary. In fact, when doing analysis, there are some rather drastic differences, but we'll look at their similarities, why they're considered both global at the same time, and contrast them to, well, if we have global fields, what are local fields? Well, given a global field, associated to it, there are infinitely many so-called local fields. And local fields are obtained from a global field by completing it with respect to each of its absolute values. Typically, there's going to be infinitely many absolute values on a field, and that's the content of this next video, in fact. Now, completions, or local fields associated to a global field, offer a much more natural place for us to perform analysis. For example, the rationals themselves are not locally compact, and when we want to do analysis on a space, we want it to be, for example, locally compact Hausdorff, to have good separation of points, as well as some commensurability, or means to do, let's say, integration. For the most basic example of the passage from global to local fields, we consider the simplest kind of global field, which is Q. We have these Q sub p, p-adic numbers, one for each prime, infinitely many of these at first, and these are what are called non-Archimedean completions. And there's a single Archimedean completion which corresponds to what's called the infinite place. And this is just the real numbers. These are Archimedean. We will look at this in more detail and understand what it means to have an absolute value, a valuation, or place on a field, and completing it with respect to that. Okay, so jumping back for a moment to zeta functions, we can discern info about the distribution and density of primes. And when I say this now that we've looked at more general sorts of rings and fields than just the integers and the rationals, they give us information about the analogs of primes, which are prime ideals, in higher up fields like number fields and function fields. So they're going to be associated zeta functions attached to each, let's say, global field. And when we study these, they give us distribution and density of primes both overall, as, let's say, the zeta function afforded that proof of infinitely many primes in general, as well as in specific constrained residue classes. What do I mean by this? So Euclid proved, this is a fact known since antiquity, that there are infinitely many primes. And this is generally the case, or there's some similarity that persists in general sorts of rings of integers. Now, much later on in the 19th century, Dirichlet proved that there are infinitely many primes not just in general, but within each arithmetic progression defined suitably. The precise statement, is that for every integer greater than 1, we can take any a that is coprime to m, and there are going to be infinitely many primes that are congruent to a modulo m. So a significant strengthening of the prior statement, and even this gets generalized several decades later by Chebotarev. In the situation for the rationals, it states that for each modulus m, the primes are actually equidistributed among residues A that are coprime to M. Chebotarev's density theorem in particular has a spectacular generalization to number fields overall, and it has very vast and profound implications. In fact, Chebotarev's density theorem was proved 100 years ago in 1922, especially why I want to get to this theorem. It's so fascinating, and this is 100th year anniversary. Okay, so no list of facts or no glimpse into number theory would be complete if we didn't mention these two. The first is the prime number theorem, which states that the primes grow at a rate that is asymptotic to x over log x, which is a surprisingly simple sort of growth for a function we wouldn't expect to grow nicely. But Gauss had conjectured this initially, and it took almost a century's worth of efforts to actually prove that the primes grow asymptotic to x mod log x, divided by log x. And there have been some efforts to get better and better approximations of how the primes grow. In fact, the Riemann hypothesis, which once again goes back to zeta functions, zeta functions have profound roles that they play in these three theorems all. If we get some fact about the Riemann zeta function in Q, that is the subject of the so-called Riemann hypothesis, which Riemann himself noticed after looking at the meromorphic continuation and the functional equation he derived for zeta of S. This is the second fact I'd like to look at. That if there are some concentration of zeros on, let's say, the real part of S is equal to 1/2 for the zeta function, this gives many strong implications for how the primes grow. So we get a much more refined perspective and much greater control on understanding how the primes behave. So with this broad overview of, first, factorization, the extent to which it holds and fails potentially in higher structures, the passage from global to local fields and characterizing the two, what that involves, as well as the analytic side of the theory by looking at zeta functions, first the Riemann zeta function, higher up analogs, and many theorems associated to the distribution and density of primes, I hope that I've shown that the analytic and algebraic aspects of number theory are in fact inseparable to some degree. So what I'd like to do is actually emphasize their connections rather than just shutting out and studying analytic and algebraic aspects separately, but noticing that they tie into one another very deeply and that we gain much more by considering them at once. Okay, so this has been a brief overview of what I'd like to cover in these following videos, this course in general. And in the next video, I'd like to start with what it means to have an absolute value on a field, which will eventually allow for us to study local fields in further generality, understand how they connect to global fields, giving total characterizations of both, and then understand much more profound aspects of the theory once we understand local and global fields. Thank you for watching this video, and I hope to see you in the ones that follow.